Hello, welcome to the Composable Extensions Task Group proposal, brought to you by the Soft Processor SIG. There are dozens of custom extensions, proprietary and non-proprietary, but as the custom extension space is unmanaged, without standards or uniformity, there's negligible reuse of custom extensions across organizations. It's unfortunate that it's so hard to build upon each other's good work. We want to make this much easier. So we propose a new task group to specify a new ISA extension plus uniform software and hardware interoperation interfaces, enabling a new, entirely optional, backwards compatible, managed subcategory of custom extensions that we call composable extensions that make it easy and routine to compose my composable extensions with yours and with others without prior coordination and without recompiling our libraries or our operating system. In all, this enables robust reuse of anyone's composable extensions and libraries. It provides a uniform software programming model across all such extensions, enabling a marketplace of reusable extensions, libraries, and hardware modules. This is especially useful on FPGAs, where you'll be able to mix and match all these third-party extensions and libraries and build a new customized SoC in an hour. Greater uniformity will improve reuse and reduce siloing and fragmentation. Here's an example to illustrate how this might work in practice. As usual, an application is built up from various separately authored software libraries. Here, these specific CX libraries can use various composable extensions custom instructions if implemented in the system hardware. So to build a system with these extensions, we will start with a catalog of reusable composable extension units, CXUs. A system manifest configures the system with a specific set of CXUs. Then a composer tool generates a processor complex, including the specified CXUs and interconnect. The composer tool also produces a system CXU map, possibly part of the device tree, indicating which composable extensions are implemented by CXUs in this system. Then at runtime, each of the application's MPEG, MXFP6, and P4 libraries use the CX Runtime API to discover whether their extension is available and then select it prior to issuing its custom instructions. By first selecting the Heart's current extension, each extension can use all of the custom opcode and CSR space, conflict-free. The linchpin of our proposal is a new extension to multiplex the custom opcode space, enabling unlimited conflict-free reuse of these opcodes. Here's how it works. On power on reset and whenever multiplexing is turned off, the system's pre-existing built-in custom instructions operate as before, unchanged. Later, an extension software library will discover if an extension is available and then select it prior to issuing its custom instructions. Discovery is performed in software in a CX runtime or a CX-aware operating system, mapping a globally unique standard CX ID into a system and Heart-specific CX selector index. Writing this index into a Heart CX index CSR enables extension multiplexing and selects the Heart's current composable extension and the extension's current state context. Then in the CPU hardware, in response to a custom opcode, the CPU partially decodes the instruction, fetches its operands, and sends an extension request with the current state ID, function ID, instruction, and operands to the selected extension. The extension performs the function and/or redecodes the instruction to address extension-scoped registers, possibly updates its state, and the CPU uses the extension's response to update a destination register and the CX status CSR. Composable extension custom instructions may be stateful. They may use CX private accumulators, registers, and register files. They may also introduce CX-specific custom CSRs, conflict-free, uniformly accessed with the usual CSR read-write instructions. We also provide uniform ways to select and manage CX state contexts. Extension multiplexing supports up to hundreds of state contexts per extension per system and any dynamic mapping from hearts to contexts, although one context per extension per heart will be common. There's also uniform, CX-agnostic operating system access control, virtualization, and context switching. So when you invent a new stateful composable extension, it just works without any kernel or driver changes. Here is a sketch of a simple C binding of a Linux programming model for composable extensions libraries. Here, the mycx library calls the CX open system call to dynamically discover if its extension is available. A 128-bit globally unique ID is the canonical name of this specific immutable version of the mycx extension contract. If the system implements mycx and if the OS grants access to it, the OS allocates a mycx state context and returns an opaque CX selector index, here called CX. Otherwise, it returns a negative index indicating no CX. This index is not unlike a file descriptor returned from an open system call. Later, when the library is closed, the CX index is closed and its state context is released. Then, for every API call into the library, if the extension is not available, the library performs a pure software implementation of the computation. Otherwise, the extension is selected. The CX select function, inlined, writes the index into the CX index CSR, which selects the mycx extension in state. Then the library issues a series of inlined mycx custom instructions to the mycx extension. Then a second CX select restores the system's built-in custom instruction behavior as required by the CX ABI. Then CX status retrieves the CX status CSR to check for errors. Here's the key paragraph of the task group charter. The task group will specify an ISA extension plus interop interface standards that enable practical reuse within a system of multiple independently authored composable custom extensions, extension libraries, and extension unit modules, while remaining backwards compatible with other custom extensions. After this presentation, we invite you to review and comment upon the task group charter on the URL above, which covers the task group's objectives, deliverables, design tenets, acceptance criteria, exclusions, collaborations, and history. Here are the design tenets found in our charter that shape and govern our design. First, composition is the overarching concern. It has to be easy, robust, routine, even boring, to add a composable extension and libraries to your system, even if they are separately authored across organizations, across decades, across different platforms and tools. Composition must just work without prior coordination or any central naming or numbering authority. Extension libraries must just work without requiring recompilation or relinking in a system built with various different organizations' composable extensions and libraries. Similarly, we want to enable modular hardware implementations of extensions that just snap into extensible processors without changing, for example, instruction decoders. In particular, this anticipates hybrid SoCs with hard processor cores tightly coupled to soft programmable logic composable extension unit cores. We require interfaces that provide uniform extension naming, discovery, versioning, state context management, and error signaling. The design should be simple, frugal, and fast. It must have a threat assessment, must not introduce side channel attacks, and must provide a means for the operating system to perform access control to extensions and state. Finally, interop interfaces and the things they interop with tend to last forever. So we require provisions for backwards and forwards compatible versioning of our interfaces and of the composable extensions, extension libraries, and extension unit hardware built with them. This slide recaps the proposed task group deliverables, ISA extensions, and new software and hardware interfaces. In our current design, the ISA changes are minimal: 0 new instructions, 4 CSRs and 2 custom CSRs, and of course, there are changes to custom instruction and custom CSR accesses. 2 new CSRs provide basic composable extension multiplexing for conflict-free custom opcodes and conflict-free CX CSRs. 2 more enable privileged code to grant or deny user access to specific CX state contexts. and 2 new per CX custom CSRs enable an operating system to uniformly save or restore any CX state context. A standard CX API provides a uniform programming model to name, discover, version, select, and use CXs. A standard CX ABI ensures correct composition of nested CX libraries and ordinary built-in custom extensions via disciplined use of the CX selector CSRs. And a new optional CXU logic interface enables glueless automatic composition of extensible CPUs and CXU hardware into processor complexes. In all, we believe this is a minimum viable set of interop standards to enable routine composition of custom extensions. Given the priv CSRs and the OS interactions, we propose the task group be homed in the priv ISA TC. At the formation of the task group, we submit the following collateral prepared by the SIG over several years of design iterations: the task group charter, a proposed specification of the extension and interfaces, including copious introductory material and rationale, a recording of a design and rationale talk introducing the proposed spec, a repository of work in progress, including the spec and implementations of various composable extension unit hardware modules. Also note there are several new products implementing an early version of the CXU logic interface, both in soft and hard processor cores. These original members of the Soft CPU SIG met to work on composable extensions throughout the pandemic years. Now looking forward, we propose to standardize the CX ISA extension and interop interfaces within RISC-V International as an official task group, with the participation of at least these companies and individual members. Darius and Jan are willing and able to be the initial acting TG chair and vice chair pending elections. But why does this CX idea merit an RVIA task group? Why not just define CX as a custom extension? Well, to avoid any conflict with other custom extensions, the CX ISA CSRs must be standard CSRs. But CX ISA alone is insufficient. Practical, routine composition requires we concurrently build a community consensus on the non-ISA interoperation interfaces, programming model, and software stack. Overall, this program is best done and really must be done within the RVIA community and running its inclusive consensus building standardization process in order to arrive at the best possible standards for the community's needs for the decades to come. Ratified composable extension standards will significantly enhance the RISC-V platform with easy extension reuse, uniform software support, and a reusable extensions marketplace. Also, composable extensions can extend the useful life of the 32-bit opcodes, even for RVIA use, conflict-free within the custom space. At the 2023 North American RISC-V Summit, Meta's Prahlad Venkatapuram called for standard ways to specify custom extensions and to unify how they are introduced to software. We believe the interfaces and abstractions we propose and will refine in this task group advance important aspects of this vision. A composable extensions framework will bring a marketplace of reusable custom extensions, libraries, and extension unit hardware. This is needed by the RISC-V soft processor ecosystem, but it's not just for FPGAs. Now, in the winter of Moore's Law, there will be tremendous pressure to add ever more domain-specific custom extensions and accelerators into every RISC-V market segment. Composable extensions will add a new, optional, backwards-compatible, uniform way to create, manage, and compose all this custom hardware and software, avoiding conflicting extension silos, helping to keep RISC-V simple, agile, and open. This is a revolutionary advance in ISA and system design, and RISC-V can offer it first. Thank you very much for your attention. We are pleased to take your questions and comments.